Hi everybody, this is Dr. Bricker here with a video for Chapter 17, Part 1. This is dealing with wave optics. So light behaving like a wave. Depending on what it interacts with, sometimes wave properties come out. Okay, so here we see a bird flying around, really interesting colors. What makes these colors exactly? Well, it turns out the feathers here, light goes through the feathers. Some of the light reflects from the front surface, some from the sort of back part of the surface. Sometimes they interfere constructively, sometimes destructively, the rays of light. And what you see here is a result of that. So really cool, cool coloring. Maybe you have seen a puddle of oil on water after it rains or something, and you see all these really cool colors. It's something called thin film interference. So sometimes the rays interfere constructively, sometimes destructively, and you get this really cool looking pattern here. Okay, so we'll talk about that in this chapter, thin film interference. Maybe you have an old DVD or a CD laying around, and you see something that looks like this. All these interesting colors too. So this comes from interference of light too. So you get this neat little pattern here. So I'll just read this. The varying colors reflected from the DVD can be understood using the wave model of light. So chapter 18, which we just did, we looked at light behaving like a ray. So just sort of traveling in a straight line, maybe bending when we went into a material, maybe reflecting from a surface. And that was good for those situations. But when you try to squeeze light through a small opening, that's when the wave-like characteristics of light actually come out. And that's what the focus of this chapter is. So we'll learn the wave model. When it applies, really when it goes through small openings, you can see wave-like behavior come out. So we'll have light go through thin films, we'll have it go through single slits, double slits, and a whole diffraction grating, a whole bunch of slits. And we'll see this wave-like behavior. Okay, so this beetle's colorful look is the result of interference between light waves reflecting from the different surfaces. So some light might reflect from the outer surface, some from a layer back a little bit deeper. Sometimes those rays interfere constructively, sometimes destructively, and you get this really neat color. So if you can see it, and you can see like green here, that's interfering constructively, and you could actually see it. So that's the predominant color there. Okay, good. If you have noise-canceling headphones, that's where you have destructive interference. You're trying to kill those that unwanted sound off. So sometimes you want constructive, sometimes you want destructive. Okay, and then here you see diffraction. So light is passing through the sewing needle, and they're slightly bent or diffracted, causing the bands that you see in this actual picture here. So we'll do a lab. The online lab that you'll do actually deals with diffraction grating, and you'll see these different patterns being formed. So when you try to squeeze light through a small opening, interesting things happen. You don't usually see this in everyday life. Sometimes you do with the thin film. You might not even realize that's what's happening. You might just think, oh, that's just the color of it. Well, the color is being made because of the thin film interference in that case. You probably have seen a CD or a DVD and seen the neat pattern, but maybe not realize what's going on there. So what you're really seeing is the wave-like behavior of light. So what exactly is light? Well, when we talked about chapter 25, we saw how we actually could produce electromagnetic waves and magnetic waves from Faraday's law. And then this wave that's produced, depending on what it interacts with, you see different kind of characteristics come out. So under some circumstances, light acts like particles traveling in straight lines, while in other circumstances, light shows this wave-like behavior. Like, for example, sound waves or water waves. So changing the circumstances, again, light exhibits behavior that is neither wave-like nor particle-like, but has both characteristics. It really just comes down to what is light interacting with, and different kind of characteristics come out. We as humans walk around, it turns out, and we'll see this in chapter 8, we have our own wavelength that's associated with us. We're just never going to be squeezed through a small enough opening to see our wave-like behavior. But in chapter 28, we'll actually calculate what our wavelength is. Okay? So we've got three different models of light. In the previous chapter, we talked about the ray model, so geometric optics, so light interacting with mirrors and with lenses, things like that. In this chapter, we're going to be talking about the wave model. So when light goes through a small opening, that's when these sort of characteristics come out. So this is all about wave optics. Okay, good. We did talk about waves, if you remember, in Physics 220. We had standing waves, and we saw some characteristics of standing waves. So take a look back at chapter 15 and 16, as it says here, when we did talk about waves, just to get sort of the basics of what a wave is. Okay, so these kind of waves, though, do not require a medium to go through. If you remember from the end of chapter 25. Back when we had like standing waves on a string, you actually had to have a string to have the waves exist. Here you don't need any air or anything like that. These waves travel in a vacuum. Okay, so the ray model we had just talked about. This is geometric optics, things like light going through lenses, interacting with mirrors, all that stuff that we just talked about. When we get to chapter 28, especially, we'll refer back to 25 a little bit, but in chapter 28 we look at light behaving as a particle, this photon model. So modern technology is increasingly reliant on this sort of idea, and quantum physics really is. Okay, so if you have a solar panel maybe on your van or on your house or something like that, you're making use of this something called the photoelectric effect, thinking of light actually as behaving as a particle. So photons don't have any mass, but under certain circumstances they sort of behave like mass. So these different quanta of light are called photons. Okay, so more about that in chapter 28. So the three models, we had just talked about ray optics in chapter 18. Chapter 17, which we're currently doing, we're looking at light behaving like a wave. And then in chapter 28, we'll look at light behaving as a particle. So that's the reason I like to do chapter 18, chapter 17, and then chapter 28, just to really look at light in those three different ways, back to back to back. Okay, that's the motivation. Okay, so water wave passing through this small opening, if you notice, it spreads out. So a wave approaches from this side, and it encounters this barrier here and a barrier here. Here's a small opening. It squeezes through and it spreads out. So this is called diffraction when that happens. Okay, so the spreading out of light going through a small opening. If the wave, in this case, water wave, was going through a big opening, you wouldn't have this happen. It's only happening because we're going through a small opening. Here's the wave going through a big opening, and you don't really see diffraction. You have a little bit maybe spreading out on the corners here, but nothing like you saw in the last picture. So when the opening is many times larger than the wavelength, it just continues in a straight path here, although you do get a little bit of shadowing over here and over here. Okay, whoops. And you can see a similar idea over here for this actual light going through these big openings here. Okay, so that this is similar to that. Okay, so whether the wave spreads out, or in other words, this new word that we have, diffracts, or travels in a straight line with sharp shadows, it depends on really the opening that we're going through. And if the opening is on the same order as the wavelength, that's when wave-like behavior comes about. Okay, so this is a little bit of a review, but we see how fast light travels, 3 times 10 to the 8th meters per second. So that's the speed of light in a vacuum. It's practically the same thing in air, so we'll go with this as the speed of light. Now the whole electromagnetic spectrum, you know, radio waves all the way up to gamma rays, that's the electromagnetic spectrum. The visible part, the part that you can actually see with your eyes, is the wavelength is something like 400 nanometers up to 700 nanometers. So all the way from red, if you want to go in increasing energy, all the way up to violet. That's the part that you can actually see. So the visible part, that's the colors of the rainbow. Okay, so if you wanted to calculate the frequency from the speed and the wavelength, this is a little review from 15 and 16. The speed would be the frequency times the wavelength. So if you solve for the frequency here, it's the speed over the wavelength. So 3 times 10 to the 8th meters per second, that's the speed of light, divided by the wavelength, 600 to the minus 9th meters, which is a nanometer. So if you had light of this wavelength, this would be the frequency. Okay, So the speed is the same, whether it's red, orange, yellow, green, blue, indigo, violet. If the speed is still the same, 3 times 10 to the 8th, but different colors, or in other words, different wavelengths have different frequencies, and you can calculate it from this formula. So the speed divided by the wavelength. Okay, good. So light waves actually slow down when they pass through materials like water, glass, and air. So in air, it doesn't slow down too much, but water and glass, the speed of light is actually less. So this is due to the interaction between the electromagnetic field, so the electric field, magnetic field, and the electrons in the actual material. So remember what the wave is. It's a electric field and magnetic field. The wave here actually interacts with the surface. Each atom in the material experiences the electric field and magnetic field, and they oscillate. And in doing so, that the wave actually slows down. So the speed of light in a material we can get from the index of refraction. Actually, this is the definition of the index of refraction. So there's no unit here. You just take the speed of light in a vacuum divided by the speed of light in the material. That's what the index of refraction is. Probably another way of thinking about this formula is to think about it like this. So speed is the speed of the wave in the material is the speed of light divided by the index of refraction. So the index of refraction is always bigger than 1. So the wave is actually slowing down. So if you take like 3 times 10 to the 8th meters per second and divided by the index of refraction, that's not my best n ever, index of refraction, you'll get the speed of the wave in the actual material. Okay, so index of refraction of glass is around 1.5. So you can see that the speed of light would be like 2/3 of what it is here if you put 1.5 in for n. Okay. All right, very good. So here's some typical index of refraction. So air exactly 1. Sorry. Vacuum exactly 1, air 1.0003. So you can see why it's practically the same thing as a vacuum. Water 1.33. We saw that when we looked at Snell's law. Same thing with glass. We did some work with glass. Diamonds all the way up here at 2.42. So light really slows down when it hits glass. But then when the light emerges from the diamond or glass or water, then it gets back to its regular speed. Okay, so there's a nice table of indices of refraction for you. Okay. Okay, so we said when light enters a material, it slows down. We were able to calculate, how much it slows down from the previous formula. Well, the thing that does not change, though, is the frequency. So when light hits this material, the speed changes. The frequency does not change. The frequency is just how often the wave is interacting with atoms and they interact with their partners. So the frequency can't change. That's sort of like the wave comes in here. It sort of shakes the hand of the material, and they shakes the hand of the next material all the way through. So you can't get any greater rate of handshakes in here than you have over here. So the frequency is the part that stays the same. The wavelength, though, has to change. So the wavelength in the material is equal to the wavelength in a vacuum divided by the index of refraction. And this is a little derivation of that. So remember, the frequency does not change, the wavelength does change. Okay? So if the speed gets lower, the same thing has to happen for the wavelength here. So take the wavelength, to get the wavelength in the material, it's the wavelength in a vacuum divided by the index of refraction. And again, the index of refraction is always greater than 1. Okay, so we've got a couple of formulas working now. We'll take a look at those in just a minute in more detail. Here's an example. Orange light with the wavelength of 600 nanometers, so 600 times 10 to the minus 9th meters, is incident on a 1.00 millimeter thick glass microscope slide. What is the light speed in the glass? Okay, so it's going to slow down. How many wavelengths of light are inside the slide? And this is similar to on your homework 17.3 and 17.6. Okay, I think we've got some information on the next slide. So from the table that we just saw, the index of refraction of glass is 1.5, or maybe you remember that from Snell's law. So we can calculate the speed. So the speed in the glass is the speed outside the glass, or in other words, the speed of light divided by 1.5. So you get 2 times 10 to the 8th, so about 2/3 of what it is in a vacuum. Okay, good. So that's the formula that we just looked at. Now, if you want to look at the wavelength, you take the wavelength in a vacuum. We already know what it is. It's 600 nanometers divided by the index of refraction of the glass, and it turns out to be 400 nanometers. So 400 to the -9th, if you want to put that into scientific notation, it would be 4 to the -7th. Now you can calculate the frequency from either part A or part B, and it's the same thing. If you do that, you'll see that. So how many wavelengths of light are in the thickness? Well, one wavelength is 4 times 10 to the -7th. So if you've got 1 millimeter, how many of these wavelengths would fit in 1 millimeter? And that's what we're doing here. So 1 times 10 to the -3rd, that's the thickness, 1 millimeter, divided by the size of one of them, 4 times 10 to the -7th, you get 2,500. So the fact that 2,500 wavelengths fit in 1 millimeter shows just how small the wavelengths of light really are. Okay, so yeah, this is really, really small. Okay, excellent. Next thing we can take a look at is the interference of light. So when light rays interact with other light rays, what happens? Okay, so let's take a look at the interference of light then. So here's light just going through a single slit, and it spreads out. So this slit is about 0.1 millimeters wide. Here's the incident laser beam, and this light actually spreads out behind the slit. Because light acts as a wave, light waves can overlap and interfere constructively and destructively. So if you had another slit right next to this one, the so-called double slit, light would be coming from each of those, and at some places the light might interfere constructively, some places it might interfere destructively. And you get an interesting pattern when that happens. So here's a double slit with incident light coming in, and you get one ray going through this slit, one wave going through this slit, and in certain spots they interfere constructively, so they add together. So if one wave looked like this and another wave was a maximum at the same location, those actually add together. If one wave is a maximum at some location and another wave is a minimum at some location, those actually cancel each other out. That's destructive interference. So again, look back to chapter 15 and 16 for that. Okay, so you've got this going on. Here's what the screen actually would look like. You get bright spots where light arrives in phase, it's called, and you actually see light. These dark fringes, that's where light, one is a maximum, one's a minimum. They kill each other off. You don't see anything there. Okay, so this is called Young's double slit experiment. So performed in 1801, so a long time ago, and going through this double slit, you could actually see this pattern. So this is proof that light behaves as a wave. If it was just behaving as a ray, light would just go through this one and go through this one. You'd see a spot here and a spot here. But it's behaving like a wave, so if it were behaving like a wave, which it is, you would expect a pattern that looks like this. So it's proof that it behaves like a wave. And it only is because you're putting it through these two small openings. Okay, so we can come up with some formulas to describe a double slit. The nice thing about this is, like if, for example, on a test, if it's a double slit problem, you only have double slit equations, and it's just a couple of equations, and that makes it a little bit easier from my perspective, because double slit problem, you've got your double slit couple of formulas, and you can solve those. Okay, so constructive interference is when they arrive in phase here. So this length, for example, R2, has to be a multiple of R1. When that happens, you get constructive interference. So let's take a look at this. The plane wave is incident. Okay, good. And here's a couple of slits. Here's the wavelength of the wave. They spread out as they go through the slits, and constructive interference occurs when R1 and R2 are different by a whole number of the wavelengths. Okay, so when that happens again, that means they would arrive in phase, and you get constructive interference. Now down here, if the path length is between R1 and R2 is different just by a half of a wavelength, in other words, this one is here, this one is here, they kill each other off at that spot, and you see a dark spot. So the bright spots are due to constructive interference. The dark fringes are due to destructive interference. Okay, and that's a synopsis of what I've just said with the dark spots there. Okay, so if you took like R2 minus R1, they're calling that delta R here. So the difference in path length, literally the distance R2 minus the distance R1, we're calling delta R here. So for constructive interference, that difference has to be a multiple of a whole wavelength. And then the destructive interference case, this delta R part has to be half of a wavelength. And then that guarantees, for the destructive case, you get this. For the constructive case, they're both maximums. Okay, here's a special term here. This is the central maximum, right in the center here. And then you get these m is equal to 1, m is equal to 2 on either side. So these are equally spaced out this way. Okay, very good. So m does not mean mass here. M is just the index that tells you which one you're talking about. Okay, good. So we can come up with a formula to describe this. So here's ray 2, here's ray 1. Now down here, this means the difference in path length, literally R2 minus R1, has to be a multiple of the wavelength. So, 1 times the wavelength, 2 times the wavelength, 3 times the wavelength. And that's where you'll get a bright spot. So a couple things here. Here is the distance to the screen. So big L is the distance to the screen. We'll come up with a couple formulas and we'll get a nice summary going on. This is theta. This is the angle that corresponds to this bright fringe here. So just from a little bit of algebra, the tangent of theta, so the tangent of theta is the opposite side, and that's what y is here, divided by the adjacent side, and the adjacent side is here. So the tangent of theta would be y over L. So if you solve for y, you get L times the tangent of theta. That's where this is coming from, just from some trigonometry. Okay, very good. So we must find the positions on the screen where this path difference length is a multiple of the wavelength. So this is a little bit of a derivation of this whole part here. Okay, a couple things to note here. Again, this just comes from the trig that we saw on the last slide. We can draw a triangle here. Okay, and here's another triangle here. So the screen is far enough away that R2 and R1 are, for all purposes, parallel to each other. So if this is theta, just from a little bit of trig, that this angle is theta, it turns out that this angle here is also theta, because we've got similar triangles going on. Okay, again, this is to derive the formula. Because point P is very far compared to the spacing, the two paths to P are virtually parallel, as we said. Therefore, just looking at the trigonometry of this, the sine of theta would be d over delta r. So again, this is theta. So the sine of theta is the opposite side, which is what we're calling delta r, right? This is the path length difference, delta r over the hypotenuse, which is actually this side. So this is the hypotenuse of the triangle over d. So do a little bit of algebra to that one, multiply both sides by little d. That's where you get this equation. So delta r is d times the sine of theta. That's just doing the trig on this triangle here. Okay, so delta r, just from this triangle, is d sine theta. This is the condition for constructive interference. So this is our formula for the double slit formula. So d sine theta is m times the wavelength, and d is the slit spacing, the distance between the slits. Okay, excellent. So d sine theta is m times the wavelength. So what does this little m here mean? This m goes along with this m. So when you're at the first fringe away from the central maximum, that would be m is equal to 1. This is the angle that goes along with that. When you're at the second fringe away from the central maximum, this is the angle that goes along with that. So theta 2 is when m is equal to 2. Theta 1 would be when m is equal to 1. Okay, so you've got each angle corresponds to the different bright fringes. Okay, so the center of the viewing screen when y is equal to 0 is equal distance from both slits. So for that case, delta r is 0 when m is equal to 0. That's just the central maximum. Okay, and then when you move away from the center, you saw in the picture, you have m is equal to 1, m is equal to 2, etc., going, up and down from where the slide is. Okay, so all those path length differences is just a multiple of the wavelength. Okay, and we could use a small angle approximation. So as long as you measure the angle in radians, the sine of theta is practically equal to theta. That's where this formula is coming from. So when the angle is small, measured in radians, sine of theta is approximately equal to theta, and you can plug that in here. You can do the same thing with the small angle approximation when you look at just the trigonometry part, and you can get this, right, the tangent of theta part. Yeah, from what we saw before, remember this was y over L, and in the small angle approximation, the tangent of theta is about equal to the to theta. So theta turns out to be y sub m over L. So you can combine this with this, and that's what you're seeing here to get the location of the bright fringes. Okay, good. So we'll have to get some practice with it, just like you've seen the whole semester probably. We've got some equations. There's really not a whole lot of intuition in these equations at all. These wave-like characteristics of light. So we really have to get some practice with the homework problems. Okay. So you can do the same kind of thing for half of a wavelength difference in path length to come up with the location of the dark spots. Here's just figuring out the interference pattern on the screen is a series of equally spaced bright lines on the screen. The fringe spacing, in other words, the distance between each of those, we can use m plus 1 and just m, put the numbers in, and you get this. This is the distance between each bright spot. So wavelength times L over D. That's the distance between, like, m is equal to 1 and m is equal to 2, 2 and 3, 3 and 4. It's all the same. So that's what this is, the distance between the bright spots. Okay, and then we can take a look at the dark fringes, and the path length difference has to be m plus a half times the wavelength. That's where we get the dark spots. We could use the relationship that we had before and come up with the location of the dark fringes. So I didn't go through all the derivation of that, but this is where the dark fringes are located. Same thing, m is just an index, 0, 1, 2, 3, etc. But this will give you the location of the dark spots. Okay, so again, here's the central maximum. M is equal to 1. It goes the same way over on the other side. M is equal to 1. M is equal to 2. Those are the bright spots. So they're equally spaced apart. Like, for example, this distance is the same as this distance. Okay, and then this formula will give you the location of the dark fringes, or the dark spots, where destructive interference occurs. Okay, good. We can take a look at the intensity of the light. So the central maximum really is the most intense spot, and then it drops off as you get farther and farther away. Okay, good. So you'd really see this if you had a set of double slits, and you could actually do this yourself. Well, I think it's on the next slide. We'll talk about how you can do it yourself in just a minute. Here's an example, though. Double slit interference pattern is observed on a screen. Okay, double slit. Hopefully you make your own formula sheet before the test. Look at the double slit section. You'll have a picture of what the double slit looks like. So we can figure out what these numbers are, right? There's a whole bunch of numbers here. What do these all mean? Double slit interference pattern, 1 meter behind the two slits. Okay, So that's the distance from the slits to the screen. That's the big L that we've been talking about. Two slits spaced 0.3 millimeters apart. Oh, so that's little d. That's the distance between the two slits. So it would be nice if it just said that, but it doesn't. You have to bring that to the problem. Okay, so that is little d. This is big L, and then have the picture in mind. Okay, from the center of one particularly bright fringe to the center of the ninth bright fringe from this one is 1.6 centimeters. Let me read that one more time. From the center of one particular fringe to the center of the ninth fringe is 1.6 centimeters. What is the wavelength of the light? So what is the wavelength? Okay, so let's see what we can do with this one. It's not obvious which fringe is the central maximum, right? They don't really tell us that. They just know that we just know the distance from one fringe that we don't know which one it is to the ninth one is a certain distance. So slight imperfections in the slits can make the interference fringe pattern less than ideal. However, you do not need to identify which is 0, because you can make use of one fact, that the distance between each fringe is delta y. Okay, just like the pictures that we've seen. Okay, so we know that the distance between these 9 is 1.6 centimeters, and there's 9 of them, so we can figure out the distance between each of them just by taking 1.6 and dividing by 9. Okay, so adjacent bright spots are 1.78 to the minus third meters apart from each other. Okay, and then using this fringe spacing, so that's the distance between each of them, we can go back to this equation 17.9 that we saw earlier to get the wavelength. So the wavelength is just d over L times this delta y. You just have to know what d is. It's the distance between the actual slits, and then this big L is the distance to the screen. Multiply it by delta y here. That's the distance between each bright spot to get what the wavelength is. So 530 nanometers. Okay, put the numbers in your calculator, it would come out to be 5.3 to the minus 7th. To make it into the minus 9th, so make this thing smaller, make this part smaller, to the minus 9th, you got to make this part bigger, so that turns out to be 530 then, times 10 to the minus 9th, or 530 nanometers. Okay, very good. So be careful on the homework. If they want the answer in nanometers, you have to put it in nanometers. Same thing with a lot of these numbers. The slit size here, you know, this is probably going to be in maybe millimeters. The wavelength's going to be in nanometers. So to be safe, put everything in scientific notation. You know, put them in a common set of units, just in meters, I would say. So it's actually not that hard to observe double slit interference. So here's a way you can do it. Place a piece of aluminum foil on a hard surface. Cut two parallel slits pretty close to each other, about 1 millimeter apart, using a razor blade. Now hold the slits up to your eye and look at a distant bright light source like a street light, and you'll actually be able to see patterns that look like this. So with your eyes, you're seeing the wave-like nature of light come out because light's passing through a small opening. Okay, very good. So it's pretty cool that that happens. And in this picture, superimposed on the diffraction pattern is a fine pattern of interference maxima and minima, as seen in the photo above, of a Christmas tree light taken through two slits in a foil. Okay, good. So you can do this if you have a piece of aluminum foil and make the wave nature of light appear to you. Here's an example problem. Two narrow slits 0.04 millimeters apart are illuminated by light from a helium neon laser. There's the wavelength. What is the angle of the first bright fringe? What is the angle of the 30th bright fringe? And this is similar to 7.78 from the homework. So take a look at the homework help video. But let's take a look at this problem. Okay, so here's the non-approximate formula. You can use the approximate one if you want to, but I'm just going to go with this one. M times the wavelength is d sine theta. Remember, the approximate one only works if you're working in radians. And okay, here's the picture that goes along with the double slit. Here's the couple of slits. theta 1 goes along with m is equal to 1. I just drew the other ones in. And then L is the distance to the screen. Okay, so what they give you in the problem is D, the slit separation, 0.04 to the minus third meters. They give you 0.04 millimeters, but milli means times 10 to the minus third. And then the wavelength is 633 nanometers, so 633 times 10 to the minus ninth meters. And we want to get theta 1, and we want to get theta 30. I didn't have room to draw theta 30 on there. I'm just going to get theta 1 for us, and then you can do the same thing to get theta 30. Okay? Good. So either of these equations actually have theta in them. Let's see which one will actually work for us. So it looks like we could just use this one, right? So m, for the first one when m is equal to 1, the wavelength is given, slit separation is given. We could get theta from this formula. So let's actually do that. M times the wavelength is d sine of theta m. And I'm going to do just the m is equal to 1 case. You could do the m is equal to 30 case. So plug in 1, you get wavelength d sine of theta 1. That's what we're looking for. So wavelength over d would be the sine of theta 1. Then you've got to take the inverse sine of both sides. So inverse sine of wavelength over d is equal to theta 1. But you can still see that. Yep. It's inverse sine of wavelength, 633 times 10 to the minus ninth meters, divided by 0.04 times 10 to the minus third meters. So the meter part cancels out, and that's how we can get theta 1. Let's see if I've got my calculator here. Again, you could do the approximate way formulas that you saw. Just be careful, because when you do that, the angle turns out to be in radians. If they want the answer in degrees, you'll have to convert it back to degrees. Okay, so whoops, I want the inverse sine of 633 EE minus ninth divided by 0.04 EE. On my calculator, EE means times 10 to the minus, or sorry, EE means times 10 to the, and then now I've got to put in the minus. Minus 3. I'm in degree mode. So really small, but not too small, like 0.91 degrees. Okay? Oh, because you see it's 9 to the times 10 to the minus 1 power, so move that over if you want to do it like that. Okay, now the only difference for the m is equal to 30 case, you would put 30 in here, okay? And then you would get theta 30. Okay, let's go back to the notes. And then we've got the diffraction grating. So the lab that we have that goes along with this chapter deals with the diffraction grating. It's similar to a double slit, it's just there's a whole bunch of slits. Looks something like this. So a multi-slit device, so just not two, a whole bunch of them. So the waves emerge from each slit in phase, and we want to figure out where you get bright spots and dim spots again. It's the same exact thing, it's just that there's more slits. Okay, so when the path difference is a multiple of the wavelength, just like we had before, the waves will be in phase, you'll get constructive interference. When the difference is a half of a wavelength, you get destructive interference, and those are the dim spots again. You get something that looks like this when you put it all together, though. So L is the distance to the screen, just like we had before. Assuming L is much larger than D, these are practically parallel to each other, and that's used to derive the formula. And you got m is equal to 0. Now note that these are not equally spaced out here. M is equal to 0, m is equal to 1. It looks something like that. Okay, these are much tighter, though, these bright spots. They're not as spread out as you saw from the double slit. So the more and more slits you get, the narrower and narrower these parts become. Okay? Good, so the same idea, a difference in the path length, so delta R is m times the wavelength, just like we did before. And when you go through the derivation, you can see that this path length difference has to be d sine of theta. Okay, so similar idea, just more slits than just two. So you get this formula then. D sine theta is m times the wavelength. It looks just like we had before. And this value of D is the same idea. It's the slit size. Usually with diffraction gratings, though, it'll tell you how many slits you have per millimeter, for example. And then you'll have to turn that into the size for just one of them. Okay, more about that in just a minute. Anyway, this gives you the if you use this formula, you'll get the angle for the bright spots. And then this part comes from just the trig, just like we did before. So these different locations, L times the tangent of theta. Okay, and then M again is called the order of the diffraction. It's just an index again. Okay, so you might get something that looks like this. Okay, so this is the Young's double slit. You can see how the intensity looks. Now this is for 10 slits, so you can see this becomes more focused. Here's for 50, and notice how these are just really, really focused. So this is more spread out. These bright spots are more intense. So in a way I think about it, it's more focused, right? It's just in a smaller region here. Okay. So spectroscopy is the science of measuring the wavelengths of atomic and molecular emissions. So we'll talk about that when we get to chapter 28. Electrons go up in energy, they drop down in energy, they give off a photon of light. So each atom has its own fingerprint. Each different element has its own fingerprint, and we could use spectroscopy to figure out really what an element is based on its emission spectrum. So atomic elements in the periodic table have a certain wavelength of light that they emit. Hydrogen has its own signature. Helium has its own signature. So we could use spectroscopy to figure out what these different wavelengths are. So if you shine, for example, mercury light through a diffraction grating, you'll get a certain pattern. You send helium light through a diffraction grating, you'll get a certain pattern. And you can use what we just developed for diffraction gratings to figure out what these wavelengths actually are. Okay, good. So you see from the formula it depends on the wavelength. So different wavelengths will have different angles, and you can see that here, right? Here's purple, here's blue. If you wanted to measure the angle, you could. These are actually separated because different angles will give you a different amount of different wavelengths will give you a different angle, and then you can see they're actually separated here. Okay, so you could use a prism to separate light into different wavelengths. You could also use a diffraction grating to do that. So when you have a CD or a DVD, you really have that. You have like a diffraction grating, light's going through it, and then when you look at it, there's a whole bunch of little holes in a CD or a DVD. The light is actually broken into different wavelengths. That's why it appears to have different colors. Okay, good. So here's a nice synopsis of these different things that we've talked about. Again, this is the approximate formula. Same thing with this one. The example that I did, I gave you the full non-approximate formula. Just be careful using these because the angle here is in radians when you do this, which is perfectly okay, but if they want the answer in degrees, you'll just have to convert it back to degrees. Okay, so you have a nice picture that goes along with this. Here's the fringe spacing. So again, when you get ready for the third test, or even when you're doing the homework for this chapter, make your own formula sheet. Definitely you need something that looks like this. Picture goes a long way. There's not a lot of intuition built into these double slit and diffraction grating ideas. And then this would be a diffraction grating. So just be careful here. This is d sine theta. That's the size per slit. Sometimes, though, they'll give you the amount of slits per millimeter. You might have to figure out what d is. When you do the lab, that'll make a lot more sense to you and when you look through the homework. Oh, as it says down here. D is equal to, for example, 1 millimeter divided by the amount of slits. That'll give you the spacing for just one of them. Okay? I think that's all I wanted to talk about today. Part 2 deals with thin film interference. Okay? Very good. As usual, if you have any questions, just email me and I'll talk to you soon. Bye-bye.